Chapter 1. Building an E&P GEOS Foundation. Section 1, Introduction. The start of any geographic information system, GIS, should begin with 1. Health. 2. Safety. 3. Security. 4. And the environment, HSSE. It is most important that we consider humans first, Earth second, and our assets last. We can use GEOS in the exploration and production, E&P, petroleum energy industry to manage our HSSE tasks and to improve our ability to bring needed energy to the people of the Earth with the least impact to the Earth. In the workflow of bringing energy to the public, it begins with the demand. The E&P industry is divided to 3 industry groups: downstream, delivering energy petroleum products to the public at their homes or a petroleum fuel station; midstream, delivering energy petroleum products from the source at the surface to the public or a processing/production plants; and upstream, the exploration of energy petroleum products from their geological source to a midstream point. GEOS, HSSE, and data management stretches across the entire lifecycle workflow. The International Association of Oil and Gas Producers had put into place several industry guideline documents, GEOS data models, and operating procedures that are vital to establishing best practices or common operating practices to help improve the implementation of GEOS in the E&P industry.
According to IOG, the oil and gas business decisions, their safety of personnel, assets, operational activities, and the protection of the natural environment, are often dependent on having complete, correct, consistent and current information of our operating locations and areas of interest. The IOG has formed a Geomatics subcommittee that is the combined discipline of survey and positioning and geospatial data management, and provides accurate positioning and mapping support across the full O&G life cycle. The Geomatics Committee aims to help members by developing and disseminating good practice, providing a forum for exchanging experiences and knowledge, supporting regulators and standards organizations, maintaining industry standard position exchange formats and a geodetic parameter database, and liaising with industry associations, users of GEOS and the underlying geospatial data by the public, engineers, geologists, regulatory, geoscientists, environmentalists, etc., must be accurate with the least amount of uncertainty to drive correct decisions. To accomplish this goal, the foundation of the GEOS and geospatial data is the Geodesy or coordinate system it is collected or represented. In E&P, a background knowledge of Geodesy is critical in modeling and decision-making. The importance of Geodesy as a discipline and application of a proper coordinate reference system, CRS, to represent area to be explored and produced cannot be overemphasized. Geodesy forms part of a wider group of geosciences commonly known as geomatics. In simplistic terms, geomatics is the science and technology of gathering, analyzing, interpreting, distributing, and using geographic information. This note will concentrate on the spatial referencing aspect. The science of geodesy, which underlies geomatics, is derived from the Greek for earth and I divide and measure. Its literal meaning is dividing, distributing and measuring the earth and refers back to ancient Egyptian land surveying techniques. A geoscientist, surveyor, geophysicist, geologist, geographer, or geomatician must all be a geodesist to reduce the impact of inaccuracies in data collection, representation and usage. The majority of the information that is of importance to the E&P business is only meaningful when associated with a location on, or near, the surface of the Earth. The word near includes the sedimentary basins and hydrocarbon reservoirs that essentially drive this dynamic industry. Spatial data, data pertaining to the location and spatial dimensions of geographical entities, runs through all E&P business processes like a thread, from the acquisition of permits, through exploration, appraisal, development and production, up to and including decommissioning and remediation. This spatial data is expressed explicitly via the use of CRS, but inadequate control of these CRS can lead to potentially serious risks for business, reputation, and HSSE. The added value of Geodesy to the E&P business lies in the assurance of the integrity of spatial data and the mitigation of the associated risks resulting from potential integrity violations. In this section, we will discuss the importance of 1. Building a strong understanding of Geodesy. 2. Establishing workflows to extract, translate and load, EDL, geospatial data. 3. Determining a HSSE plan that includes keys to reduce our impact on the Earth to bring energy to the people of the Earth. The E&P industry can best be understood in a workflow format. Downstream. 1. Public needs energy. 2. Public purchases energy from suppliers. 3. Energy is provided through a series of pipelines directly to homes and businesses or transported to a fueling station. 4. Suppliers purchase energy from producers or own production sources. 5. Energy is processed, refined, separated, mixed, and marketed at facilities. 6. Facilities management is used in processing/refining and/or fueling stations. Midstream. 7. Energy is provided to processing/refiners and/or fueling stations with larger main or trunk pipelines from gathering stations of smaller flow pipelines or via transportation trucking/rail systems. 8. Energy from natural gas and liquid oil petroleum products are separated and stored at exploration well locations at the surface before transportation via trucking or gathering/flow pipelines upstream. 9. Fluid injection to stimulate O&G flow or manual pumping to lift or push O&G products to well location are applied. 10. Wells are permitted and drilled within casings to separate groundwater aquifers, and tested to obtain O&G products. 11. Sites are selected and well pad is built with surface disturbance agreements with any needed permits. 12. Preliminary well and well bores are designed with expected production to cost. 13. License, lease, fee, joint operation agreement, or working interest agreement is obtained to explore and produce minerals at specific depths and/or fields. 14. Basins, depth horizons, and/or fields are analyzed for potential investments by E&P operators. Section 1.1 Risk Management. According to GEOG, the oil and gas industry has hazards, risks and opportunities that are inherent to its assets, activities, operational locations and products. Using a standardized approach to risk management has the advantage of accounting for the different sources and types of risk found in both client and contractor activities. Before entering into a contract and starting any operation or project activities, it is important to establish the context and assess the risks. There should be a clear understanding of the technical objectives, scale of operations, geographic location and time frame. All potential consequences, beneficial and adverse, should be assessed in terms of hazards, effects, aspects or threats, and the likelihood and potential severity of a consequence used to assess the level of risk. The risk profile from the initial assessment of the proposed contractual scope of work is used to broadly determine the HSSE management system, HSSEMS, needed to control the risks. The sources and risks identified may be updated in later phases following these activities to ensure the risk profile is up to date. Clients and contractors should both have robust assurance mechanisms in place. An assurance mechanism is an activity, process or action, such as an audit or verification activity, that provides confidence and confirmation that an HSSEMS, or any part of an HSSEMS, is achieving its purpose and expected performance. The type and degree to which assurance mechanisms are implemented during each phase will vary based on the HSSEMS governing or regulating the work, such as the client, contractor, or a combination of the two, the risks associated with the work, and the risk tolerance of the individual client company. A HSSEMS plan has both how the GEs will be used in HSSE activities and how the GEs, Geodesy, and geospatial data management will be performed to ensure highest performance from information and reduce risk. Everyone in the workflow is responsible for identifying the inherent hazards, effects, impacts and threats and assessing the sources and types of risk and opportunities involved in conducting the work. This will aid both the all in developing risk controls/barriers to reduce risks and ensure protection of all personnel, assets, reputation and the environment. Section 1.2, Continuous Improvement. The Plan-Do-Check Act cycle for continuous improvement should be used when designing assurance mechanisms for each phase. Verification, monitoring and audits are required of the HSSEMS plan. Final evaluation and close-out centers around performance review meetings, final reports, capturing lessons learned and sharing the lessons, etc. and are key aspects of continuous improvement. To build success in any plan is to have involvement and support from everyone at all levels. This is best done by establishing a governance group to establish how a SIMS plan should be designed, implemented and improved. This governance group should decide on data and software standards, assessment, budgets, purchases, data subscriptions, upgrade/update paths, and common practices. Transparency and user surveys can be used to establish user involvements. Ultimately, leaders need to support and agree on user-defined practices for organizations with written policies. It is best if GEOS is managed by a central group because it stretches the entire workflow, unlike other professions that are only involved in their areas. For example, an engineer is less likely be involved in subsurface basin analysis, or geologist would not be involved surface owner disturbance agreements. Information technology groups are often thought to be the ideal group to implement a GEOS based on the heavy IT infrastructure requirement, but they are not the ideal group to implement the power of GEOS in analytics. GEOS should be owned by all professions involved in the E&P, geologist, geographers, engineers, legal, regulatory, environmental, facility management, etc. Therefore, a governance group that incorporates all stakeholders is best in establishing successful continuous implementation. Section 1.3 Implementation. Effective implementation of the defined scope of work, including meeting the governance group for the HSSE and GEOS requirements, is the ultimate goal of the contracted activity. This requires that this guide be implemented company-wide so that appropriate, effective risk controls are consistently applied, regardless of the contracted scope of work. Policies, standards, processes and procedures that make up the client HSE requirements, including the HSSE and GEOS with associated documents, are key to implementing the selected controls for the scope of work. These should be clearly defined, documented and well communicated across to everyone at all levels. Effective implementation needs a disciplined and capable workforce, with a shared commitment to carry out the work safely, responsibly, reliably and in conformance with the plans and procedures developed during the implementation of this guide. Responsibilities, accountabilities and authorities need to be maintained to effectively implement the determined standards. Section 1.4 Basic Principles of Geodesy. Coordinates belong to a coordinate system. A coordinate system, CS, describes the mathematical rules governing the coordinate space, including the number of axes, their name, their direction, their units, and their order. When coordinates are used to describe position on the Earth, they belong to a coordinate reference system. A coordinate reference system, CRS, is a coordinate system which is referenced to the Earth. The referencing is achieved through a datum, details to follow. The surface of the Earth is irregular, see Figure 1, and is therefore difficult to calculate on directly. Instead, surveyors use a model of the Earth for their calculations. Numerous models exist and any one model may have several variations in position or orientation relative to the Earth. Each variation leads to a different CRS. In general, if the coordinate reference system is changed, then the coordinates of a point change. Consequently, coordinates describe location unambiguously only when the CRS to which they are referenced has been fully identified. OGP has created a database of these CRS to regulate and minimize the risk of applying the wrong systems or component parameters. Helmert, 1880, defined geodesy as the science of the measurement and mapping of the Earth's surface. As most of the Earth's surface is shaped by gravity, the determination of the geometric aspects of the Earth's external gravity field, the geoid, is a key element of geodesy as a science. The surface of the Earth with its topography is far too irregular to be a convenient basis for computing position. Surveyors reduce their observations to the gravitational surface, which approximates mean sea level. This equipotential surface is known as the geoid. It is approximately spherical, but because of the rotation of the Earth, there is a slight bulge at the equator and flattening at the poles. In addition, because of the variations in rock density that impact the gravitational field, there are many local irregularities. These factors make the geoid a complex surface. Ellipsoids, also known as spheroids. To simplify computing of position, the geoid is approximated by the nearest mathematically definable figure, the ellipsoid. The ellipsoid is effectively a best fit to the geoid. However, there are numerous ellipsoids available, each of them uniquely named and defined either based on their semi-major axis, semi-minor axis or, more usually, a ratio of these axes called inverse flattening. Approximation of the geoid by a reference ellipsoid could traditionally only be done locally, not globally, and this limitation led to the existence of many ellipsoids, each with a different size and shape. Some of these ellipsoids approximated different parts of the surface of the geoid, whereas others expressed the increasing knowledge about the Earth's shape and size over time. Now many of these ellipsoids have become obsolete, whilst others have become enshrined in national mapping systems, such as the Airy ellipsoid from 1830, which still forms the basis of the British national grid. A few important ellipsoids are highlighted in Figure 2. Note they sometimes have aliases and a date reference which can be confusing, hence the evolution of the OGPZ-PSG dataset. Geodetic Datums. A geodetic datum defines the position and orientation of the reference ellipsoid relative to the center of the Earth, and the meridian used as zero longitude, the prime meridian. The size and shape of the ellipsoid are traditionally chosen to best fit the geoid in your area of interest. A local best fit will attempt to align the minor axis of the ellipsoid with the Earth's rotational axis. It will also ensure that the zero longitude of the ellipsoid coincides with a defined prime meridian. The prime meridian is usually that through Greenwich, England, but historically, countries use the meridian through their National Astronomic Observatory. This best fit is centered on a position on the Earth's surface within the area of interest, e.g. the Helmert Tower at Potsdam, near Berlin, was used for the European datum 1950, ed. 50. A geodetic datum is inextricably linked to the generation of geographic longitude. Coordinates. Geographical coordinates, latitude and longitude. The position of a point relative to a geographical coordinate reference system is described on the CRS ellipsoid and is generally expressed by means of geographical coordinates, latitude, phi and longitude lambda, as shown in Figure 1. These are angular expressions related to the equator and the prime meridian, usually, but not always, the meridian passing through Greenwich, London, these being the 0 degrees references for the NS/EW direction. For example, a typical position would be expressed as latitude 57 degrees 30'15 N, longitude 3 degrees 40'20 W. Note that a position with a latitude south of the equator or longitude west of the prime meridian is sometimes shown as negative, e.g. 3 degrees 40'20. It is very important to appreciate that latitude and longitude are not unique and are therefore entirely dependent on the chosen geodetic datum, see following section. Conversely, any given values of latitude and longitude can refer to any geodetic datum. Heights above the ellipsoid are not of much practical use because it is easier to measure height from or to the geoid. This will be discussed later on. In summary, as with any other type of coordinate, geographical coordinates in themselves do not describe position unambiguously, the associated CRS must be identified. Without knowledge of the geodetic datum, the latitude and longitude of a point will have an inherent ambiguity of up to 1,500 meters, this being the maximum positional effect caused by the irregular shape of the geoid. An ambiguity of this magnitude may be disastrous for achieving E&P business goals. It may even lead to very severe HSE incidents by e.g. drilling into a shallow gas pocket believed to be hundreds of meters away. Each of the many models, ellipsoids, may have several determinations of its reference to the Earth, each resulting in a different geodetic datum. For example, the International 1924 ellipsoid is referenced to the Earth at Potsdam for the European 1950 datum, but also referenced to the Earth near Rome for the Monte Mario 1940 datum used in Italy. Because of the irregularities of the geoid, a point has coordinates referenced to European datum that differ by several meters from coordinates referenced to Monte Mario datum, despite both datums using the same ellipsoid. Similarly, if the model is changed, a different ellipsoid adopted, even when the reference point is retained, coordinates of positions away from the reference point will differ. For more detail see OGP Guidance Note 13, Advisory Note on Derivation of Geodetic Datum Transformations. Other types of CRS will be discussed later. Coordinate transformations. In order to merge points such as surface well locations, whose geographical coordinates are referenced to one particular CRS, with other points based on a different CRS, one of the two datasets must be transformed. It is possible to measure and calculate the displacements, rotations and scale differences between them. There are numerous different methods of transforming coordinates and more detail can be found in OGP Guidance Notes 7 and 13. Various C&P companies adopt different CRS to store geo-referenced data in their corporate databases. It is therefore quite common to have to transform datasets to suit the recipient's prescribed CRS, prior to sharing data with other operators or submitting information to regulatory bodies.